My name is Vineet. I'm the co-founder of Succeed Easy Tutorials. In this channel, we post content on mathematics, English, and soft skills. In this video, I shall take you through logarithms. So we shall discuss the concept of logarithms, the arithmetic operations involving logarithms, and also how to find the log and anti-log of a number using log tables. So guys, if you are not allowed to use a scientific calculator, you will find this video extremely useful for you. At the end of this video, I promise that you will have a very fair idea on how to use logarithmic tables to do complex calculations. We shall also discuss some of the arithmetical operations using which you will be able to convert difficult arithmetic operations into simple logarithmic operations. I would request you to please stay till the end of the video to make the best use of this video. Let's begin with the question, what is a logarithm? Logarithm is another way to express exponents. For example, 2 to the power 3 is 2 times 2 times 2, that is equal to 8. In this case, 3 is the exponent or the power or the index. So 2 to the power 3 equals to 8. And therefore, this is an exponential function. 2 to the power 3 equals to 8. We can convert that into a logarithmic function by saying that log of 8 to the base 2 equals to 3. This log of 8 to the base 2 is read as log base 2 of 8 or log of 8 to the base 2. In simple words, log of a number to a specific base is the power to which the base must be raised so as to get the number. In general, log of a to the base b is equal to c is equivalent to saying that b to the power c is equal to a. So logarithmic form is log of a to the base b equals to c, and exponential form is b raised to c is a. Log of 9 to the base 3 equals to 2. This implies that 3 raised to 2 will be equal to 9. Similarly, log of 1000 to the base 10 equals to 3 means basically that 10 to the power 3 is equal to 1000. Now you can go this way or you can go this way, right? That means you can say that if this is true, then you can say that log of 1000 to the base 10 will be equal to 3. So in general, log of a to the base b equals to c is equivalent to b to the power c equals to a. In this case, a is called the argument, b the base, and c the exponent. Please notice that the base of the logarithm in both the functions, logarithmic as well as exponential, it remains the same, right? So the base of the logarithm is the same as the base of the exponent. Another point, base b is greater than 0. That is, it is positive in an exponential function, right? Why so? Because in an exponential function, the base is always defined to be positive. Okay, so the base is always positive. Remember that. Now, the argument a is greater than 0. That is also positive. The reason is that if b is positive, then you raise a positive number to any other number, number c. You raise a positive number to any number c. If c is positive, it is going to positive raised to positive will give you positive. And positive, even if you raise it to a negative power, that will still give you positive. Let me elucidate this a little bit. Let's say the base is b, as we have already taken the base as b. What I mean is that b to the power 0 is equal to 1. If b is positive, then you raise b to a positive number. You are going to end up with positive, obviously. But if b is negative, let's say it is minus 2. If you raise it to, let's say, a negative, base is always positive. If you take it as base as 2, positive 2, and you raise it to a negative power, let's say minus 3, then that is the same thing as 1 upon 2 to the power 3. So that is also going to result into positive, right? So I hope this point is clear, that base is always positive because it is in an exponential function. The base is always defined to be positive. And a, the argument, is also positive because base raised to, whether positive or negative, is going to end up with positive. So remember that argument will also be positive always. And base is never equal to 1. The reason is that if you take, for example, log of 8 to the base 1 equals to, let's say, any number x, then in that case, 1 to the power x is going to be 8 as per the definition that we just saw, the conversion between exponential and logarithmic functions, right? So 1 to the power x is not equal to 8. This is not true, right? 1 raised to any power cannot give you 8, correct? So base cannot be equal to 1, all right? Please notice, if you want, you can take a screenshot. Third point, log of a number to the base 1 or to the base 0 is not defined. Please note that. But if b is any base or any number other than 0, then b to the power 0 is equal to 1. We can convert this exponential function into logarithmic form. We can say that log of 1 to the base b equals to 0. So what we get is log of 1 to any base will be equal to 0. But note that log of 0 to any base is undefined. Please note. So log of 0, because in this situation, why is it undefined? Because you cannot have a situation in which b raised to any power x is going to end up with 0. Got it? So this is undefined. This is not correct. Okay, please note that it is undefined. Let's now look at some arithmetic operations involving logarithms. The goal is to make our calculations faster and simpler. Let's quickly look at some of the rules. Log of m into n to the base b equals to log of m to the base b plus log of n to the base b. Log of m by n to the base b equals to log of m to the base b minus log of n to the base b. So this is the product form. This is the quotient form. Now the exponent form, log of m to the power n or m raised to n, okay, to the base b equals to n. The exponent comes here, okay, n times log of m to the base b. Fourth rule, log of pth root of m to the base b equals to log of, it is the same thing as log of m raised to the power 1 upon p to the base b. And going by the third rule, we know that we can put the exponent 1 by p in terms of multiplication. So we can put it here 1 by p times log of m to the base b, okay? The fifth rule, change of base. If you have to change the base, then log of m to the base b will be the same thing as log of m to the base k upon log of b to the base k, where k is any arbitrary number. So the base changes. In this case, it becomes, instead of b, you have the k as a base in this expression. Okay, let's do now example of usage of rule 3. So let x be equal to 1.025 raised to the power 20. Then log of x will be equal to log of 1.025 raised to 20. We're using rule 3. We know that we can put that as equal to 20 times log of 1.025. Okay. Now, please note that right now we are considering common logarithms. So everywhere the base is 10. It is the base 10 logarithm that we are doing right now. Okay. So before that, let's understand the types of logarithms based on the base, okay? So common logarithms, natural logarithms, binary logarithms, and log to base b. These are the kind of logarithms that are in use. And common logarithms, the base is 10. For natural, the base is e. E is Euler's number. It's a constant, right? So 2.718, that's it, right? That's an irrational number, and it goes on. Base is e. For natural logarithms, for binary, the base is 2, and log to base b, obviously, the base remains b. It could be anything, base b, as per the rules that we just discussed in the previous slides, okay? So the way to express the common logarithm is you write lg of x, or you write log of x, or you write log of x to the base 10. Natural logarithms, you write it as ln x, or log of x to the base b, to the base e, I beg your pardon, okay? So remember this, lgx or log x. So wherever you see log x, okay, that time, please note that it will be log of x to the base 10. And wherever you see ln x would mean you are talking about the natural logarithm. Log of x to the base b is, obviously, it's very clear that it is to the base e, okay? And binary log, you write it as lbx. And for log to the base b, you write log of x to the base b. Please note that common logarithms are mostly used in engineering. By the way, these notations were all the ISO notations. Common logarithms are mostly used in engineering, natural logarithms in mathematics, and binary logarithms in computer science. Let me give you a glimpse of the logarithmic tables. So the logarithmic tables look like this. See, from 10 to 99. The rows, these are the rows, starting with 10, going right up to 99. And it has columns from 0 to 9. All right. So there are 10 columns there. And the mean difference table has columns from 1 to 9. Okay. So have a close look at this. We shall be using this for doing our calculations. These are the common logarithms or the base 10 logarithms. Okay. The anti-log table looks like this. It starts with 0.00 row and it goes up to 0.99 over here. Okay. The columns remain the same as the log table, 0 to 9, and the mean difference table also remains the same from 1 to 9. All right. Okay. Now let's do computation using log tables. Let's begin by finding the value of 1.025 raised to the power 20. So let x be equal to 1.025 raised to the power 20. Taking log of both sides, we get log of x to the base 10 equals to 1 log of 1.025 to the power 20. All right. They are all common logarithms to the base 10. So using rule 3, we can put log of x to the base 10 as equal to 20 times log of 1.025 to the base 10. The exponent comes here and gets multiplied by with the base. In this case, it was log of 1.025 to the base 10. All right. I hope you are clear on this. So how to find the log of 1.025 and, to be precise, to the base 10. All right. So let's understand the process now. Let's look at the steps. First, you express 1.025 in scientific notation, also called the scientific form or the standard index form or the standard form. All right. So I intend to make a separate video on scientific notation very soon. But for the current purpose, to help you move ahead on this part of the calculation process, let me tell you very briefly that to put a number in scientific notation, what you do in very simple terms, you take the first significant digit, okay, and then put a decimal after that. Let other numbers or other digits be there in the decimal, and then express that in terms of power of 10. Okay, we shall do a couple of problems to make this point very, very clear. But for now, please be with me and just understand the process. Okay, so 1.025, you express that as 1.025 into 10 to the power 0, because 10 to the power 0 is 1. And I had to put this in terms of power of 10, right? 1.025 already has a decimal after the first digit, and everything else is expressed as a decimal part. So I was not needed to multiply it by 10 raised to any other power other than 0, because multiplying that by any other power of 10 would have changed this value, right? I mean, I need to get the same thing as what it is already visible, that is 1 point something, right? So I multiplied it by 1, that is 10 to the power 0. Now the exponent of 10, that is the power of 10, okay, the index or the power or the exponent of 10, it gives me the characteristic of the log, right? And what is characteristic? Characteristic basically is the integral part of the log. I can also call it the whole part. I get 0 as the characteristic for log of 1.025 raised to the to the base 10. Okay. We now need to find the mantissa. Mantissa, what is mantissa? Mantissa is basically your fractional part of the number. A number is made up of a whole part, as in, let's say 2.37. In this, 2 is a whole part. It is the same thing as saying 2 plus 0.37. All right. So this is the whole part, and this is the fractional part. Okay. All right. So I hope you understand this already. So ignore the decimal. Now the second step is that ignore the decimal. The number was 1.025. So now ignoring the decimal, we get 1025. So in the log table, look at the row that starts with 10. The first two digits, 10, Then note the number that is at the intersection of 1 0 row and the 2 column. That is this third digit. Look at this log table. 1 0 row and 2 column, that is 0086. The intersection is 0086. So we get 0086. Now look at the mean difference table for the fourth digit. What was the fourth digit? It was 5. So look at the mean difference table for the fourth digit. Mean difference table gives you the fourth digit. So it was 21. So now you put the numbers 0086 from here and 21 from the mean difference. Add them. You get, what do you get? 6 plus 1 is 7, 8 plus 2 is 10, 0, 1. So you get 0107. Now this 0107 becomes your mantissa for the log, or the fractional part for the log. Step 3, add characteristic and mantissa to get the log value. So characteristic was 0, mantissa was 0.0107. You get 0.0107, right? So log of 1.025 to the base 10 equals to 0.0107. Look over here. We had put log of x to the base 10 was equal to 20 times log of 1.025 to the base 10. We got this value. So we now need to multiply that by 20 to get the value of log x to the base 10. So log of x to the base 10 will be equal to 20 times log of this to the base 10. That means 20 times 0.0107. That is log of x to the base 10 equals to 0.2140. Now, every time I do not actually need to say base 10, we are writing it as log x, and that basically means that we are working on common logarithm. So sometimes we may avoid writing that, and we can also avoid saying that often. Okay. Now to find x, we need to take, so by the way, we got log of x as 0.2140. So now to find x, we need to take the anti-log of 0.2140. How do we find the anti-log? So log x equals to 0.2140. That basically means that actually 10 to the power 0.2140 is x, but this will be very tedious process. And of course, this is just to show you that, look, actually the value of x will be this. That is 10 raised to 0.2140. That will be x. This will be the actual value, but we don't need to calculate this. The anti-log table does the work for us. Okay, let's see how. Steps to find the anti-log. So x is equal to anti-log of 0.2140. Step 1, the whole integral part gives the characteristic, that is c equals to 0. How? See, the integral part of this number, that tells us, that gives us the characteristic of the anti-log. So c is equal to 0. That is, characteristic is equal to 0. Now hold on to this. We will use this later to put the decimal. I'll explain that a little bit later. Now, step 2 is focus on the mantissa, that is the fractional part. So the fractional part here is 0.2140, right? The first two digits are 0.21, the third digit is 4, and the fourth digit is 0. So in the anti-log table, go to the row that begins with the first two digits, meaning 0.21. Okay. Note the number that is at the intersection of 0.21 row and the fourth column. That means this third digit. All right. So let's look over here. The 0.21 row and the fourth column, the intersection is 1637. Okay. So since the fourth digit is 0, let us recheck that. The fourth digit is 0 over here, right? So since the fourth digit is 0, we can ignore the mean difference table, because look, there is no column which starts with 0 in the mean difference table, right? So wherever fourth digit is 0, we can ignore the mean difference table. So step 3 is, now look, in step 1, we had got the characteristic as 0. So there comes the usage. Add 1 to the characteristic that you obtained in step 1. Okay, so you get 0 plus 1, that is characteristic was 0, so you get 0 plus 1 equals to 1. This tells you where to put the decimal. So put decimal after the first digit from the left. What you got till now was 1637, isn't it? So starting from the left, you need to leave one digit from the left. This is what you get when you add 1 to the characteristic. Okay, so leaving one digit from the left, you get 1.637. That becomes your anti-log. Thus, x is equal to 1.637. That is your final answer to the question. X is equal to 1.025 raised to the power 20. Now, let us see whether this is close to the actual. Let me just pull up my calculator, and I hope my calculator is visible to you right now. I'll put 1.025, 1.025 as x, and I'm raising it to 20. So what I get? 1.638616 and so on. So 1.638 I pick up, look over here, 1.638, and the answer that we got using log was 1.637, right? So it is pretty darn close, isn't it? All right. There might be some errors when you calculate using a calculator and when you get your answers using log. There might be some differences, okay? But those differences are generally minimal, okay? And it depends on so many factors, including the number of significant digits that you take. All right. By the way, I intend to make another video on significant digits. So we'll discuss more about it as we go. But for now, please stay on and let's discuss further. So, but before taking up further questions, let's understand a bit more about characteristic and mantissa, right? So what is characteristic and mantissa? Okay, let's discuss a little bit. I introduced the concepts to you in the prior example, but let's discuss a little bit more about it. Okay, so an important property of common logarithms, that is base 10 logarithms, is that the fractional part of the logarithms of numbers greater than 1 that differ by a factor of a power of 10 all have the same fractional part. Okay, this is a bit confusing, but if you focus on it and reread it, couple of times, maybe you will be able to make a sense of it much better. Okay, so see, I repeat, the fractional part of the logarithms, okay, of numbers greater than 1 that differ by a factor of a power of 10 all have the same fractional part, okay, that differ by a factor of a power of 10. This is important, right? So please try to make sense of it, okay? This fractional part is called the mantissa. Log tables depict only the mantissa. Second point is that the integral or integer or non-fractional or whole part of the logarithm is called the characteristic. To find the characteristic, just count the number of places that the decimal point must be moved so that the decimal point is immediately after the first significant digit. This is what I had explained to you before as well, but now let's elucidate this a little bit more. So log of 1500 to the base 10 is the same thing as log of, I write, if I were to put a point over here after 1, then that means I needed 1.5. Now that means how do I get 1.5 out of 1500? I will divide 1500 by 1000 so as to get 1.5, isn't it? So if I divide it by 1000, I'll multiply the number by 1000 so as not to change the value of the expression, right? So I get 1.5 times 10 to the power 3, right? Now, using the properties of log, we know that what is the log of m into n to the base 10? That was equal to log of m to the base 10 plus log of n to the base 10. So in this case, m is 10 to the power 3 and n is 1.5, right? This is your m, this is your n. So you can relate to the formula that we did in the prior slides, right? So we get this part, log of 10 to the power 3 to the base 10 plus log of 1.5 to the base 10. So this can be expressed using rule 3. This part can be expressed as 3 times log of 10 to the base 10 plus log of 1.5 to the base 10, right? Now what is log of 10 to the base 10? This is equal to 1. Why? Because 10 to the power 1 is equal to 10. So log of 10 to the base 10 equals to 1. That's the conversion, right? Exponential to logarithmic form. So this gives us 1. So 3 times 1 plus log of 1.5. Now I have deliberately written 00 over here. Reason is that log system works on those 4 digits. The standard logs that I'm using, they're all based on this 4-digit system, 2, 1, and 1. That's why, right? So just keep this in mind. Okay. So you get 3 plus. Now the value of log of 1.500, okay, it's 0.1761. How? 15 row and 0 column. 0 is the 4-digit is 0, so the mean difference column would be ignored. And intersection of 15 row and 0 column gives you 1761. The characteristic for, in this case, will be 0. The characteristic will be 0. Why? Because 1.5 can be expressed as 1.5. We have already seen that before. Can be expressed as 1.5 into 10 to the power 0. So this gives you the characteristic, and that's why you are going to get 0.1761. All right. So since we had already discussed that before, I have not calculated that separately, and this is just an indication to you. Okay. So you add 3 plus 0.1761 so as to get 3.1761. Okay. I hope you are clear till here. Now, by the way, log of 1500 to the base 10 equals to 3.17609 using calculator. Okay. And if you round it to 4 decimal digits, then you are going to get this 9 is greater than 5. So 0 will be 0. You will have to add 1 to the 0 so as to make it 3.1761, right? So you get 3.1761. Okay. Using a calculator also, you get this, and the value that we got using the log table, exactly, it matches this, right? So you see the log tables, they work. Okay. So in 1500, we had to move three digits towards left so as to get the decimal after the first significant digit, and therefore the characteristic was 3. You remember that. This is a repetition. Okay. We have already discussed that. Now, there could be 3 situations for characteristic. What are those 3 situations? You may have to move to the left to place the decimal. Okay. Example, in 1500, which is a positive number, the characteristic, you had to move to the left to place the decimal. Okay. Because you wanted the decimal here after 1, after the first significant digit, to put it in scientific notation, right? In that case, we saw that the characteristic is a positive integer. Why? Because you divided it by 10 to the power something, and then you multiplied it by 10 to the power something. So that the power of 10 was positive, and that is why the characteristic was positive in this case. Another situation is that you need not move to place the decimal. Example, in 1.500, the decimal is already there, right there after the first digit. Okay, so you can just put this as equal to 10 to the power 1.500 can be put as 1.500 into 10 to the power 0. So in this case, the power of 0, the power of 10 is 0, and hence the characteristic is 0. Okay. The third situation is then when you might need to move to the right to place the decimal. Example, in 0.0150, you need to move to the right to place the decimal. Why? Because look, when you will study about the significant digits, you will realize that the preceding zeros, they do not count as significant digit. In this case, I will need to move the decimal over here. After 1, I want the decimal, right? How do I do that? So if I were to move the decimal to the right, that means 0.015, and I want to move this decimal to the right, I'll have to multiply this by 100, isn't it? 0.015 times 100, the decimal is going to move 2 places to the right. That means it will come after 1. But if I have multiplied this expression by 100, then I have to divide it by 100 so as to keep the value the same. That's why. So this multiplication gives me 1.5. That was my desired expression. Okay, the desired way. So I got that. But division by 100, that means multiplication by 10 to the power minus 2. I hope I'm clear on that. And in this case, the exponent of 10 is -2, and that's why the characteristic is -2, which is a negative integer. So please keep an eye on that. If you want, you may take a screenshot of this, and you may need the rules to come back and do to do the problems on your own. So I suggest you please take a screenshot of this. Okay. Now, what are negative logarithms? See, as seen in the third situation. Okay. For positive numbers less than 1, that is for a number x, where x is between 0 and 1, right? X is between 0 and 1. Log x is negative. Okay. We have seen that in the third situation. Look at this. Log x will be negative. Why? Because the characteristic here is negative. So you will add this negative characteristic to a positive integer, which you will see later, the Mantissa part, but that you will end up with a negative number, right? So as seen in the third situation, for positive numbers less than 1, that is numbers between 0 to 1, the log x is negative. We usually express a negative logarithm as the sum of a negative integer characteristic and a positive mantissa using bar notation. All right. Now, what is this bar notation? I'll explain that. The advantage of doing this is that we avoid the requirement of having separate tables to convert positive and negative logarithms back to their original number. All right. Let's take an example. Log of 0.0150 to the base 10. That is equal to, now in this case, we know that this number expression, the characteristic would be -2. We have seen that before, right? I need not repeat that, okay? And we have also seen that the log of this part, 1500, okay? We have seen that it before, right? 15 interaction of 1, 5, and 0, it gives us 1761, right? So we have seen this. So I'm taking values from whatever we did before, okay? So log of 0.0150 to the base 10 is approximately equal to, this is the bar that I was talking to you about, okay? So this is read as bar 2.1761. It is read as bar 2.1761. This part, bar 2.1761. This is how you read it, okay? And actually, if you take -2 and add +1761, you are going to obviously get -1.8239, okay? What is this? What is the meaning of this bar 2.1761? It means that the characteristic 2 is negative. This bar means that the characteristic 2 is negative, while the mantissa 0.1761 is positive. Please keep this in mind. Let's continue with some of the other calculations. Let's take another example. Let's do log of 1.03 to the power. Let's find the value of 1.03 to the power 20 using log tables, okay? So let's take x as equal to 1.03 to the power 20. Taking log of both sides, we get log of x to the base 10 equals to log of 1.03 raised to 20 to the base 10, okay? Using the rule 3, we know that that will be equal to log of x equals to 20 times log of 1.03. All right, so now we need to find log of 1.03 to the base 10. 1.03 is that second type in which you need not move the decimal, right? It is already placed after the first significant digit. You can just put this number as equal to 1.03 into 10 to the power 0. And the exponent of 10, that is 0, that becomes your characteristic, right? So let's now find the mantissa, that is the fractional part. What's the number? The number is 103. You can take this number as 1030, okay? So the first two digits will be 10 and the third digit is 3. So first two digit is 10, third digit is 3. Look at the intersection. What you get is 1, you will get 0128, okay? Fourth digit is 0. So you ignore that mean difference table, okay? So what mantissa you get is, you get 0.0128. Mind you, this 0128 is the fractional part. That's why you can put this decimal over here, okay? All right. So now characteristic was the whole part. Characteristic, we already got that as equal to 0. So add characteristic to this number 0.0128 so that you will get 0.0128. That's the value of your log of 1.03. All right. But log of x was equal to 20 times this value. So multiply that, you will get 0.256. Okay, so x is equal to, so log x equals to 0.256. So x is equal to anti-log of 0.256, right? Again, I have put a 0 over here because, as you know, we are working on 4 decimal digits. Okay, so the fractional part is 0.2560 and the whole part of this is 0. The whole part of the anti-log, this part, the integral part, that gives us the characteristic of the anti-log. In this case, it is 0, so the characteristic is 0. Now, in the anti-log table, note the value at the intersection of the first two digits, that is 0.25 and this 0.25, and the third digit, that is 6. Okay, so what do you get? 0.25 and 6, you get 1803. Since the fourth digit is 0, you ignore the mean difference table. What you get is C equals to, now look, C was equal to 0. All right, let me repeat. You get 1803. Up to here, are you clear? Okay, since the fourth digit is 0, ignore the mean difference table because there is no column which starts with 0 in the mean difference table. All right, now let's go back. The characteristic was 0. And this helps us to put the decimal, right? In whatever value you get after you find the mantissa part, right? So characteristic was 0. Add 1 to the characteristic. You get 0 plus 1 equals to 1. So put the decimal after one digit from the left of 1803 so as to get 1.803. Okay, so this is the repeat of the process that we followed in the prior example. Okay, so there will be some, time and again when we do that, I think that will be the time when you will, this concept will get reinforced. Okay, so mind the process. In case you want, you can make notes, okay, so that you do not forget the process. All right, and I hope you have taken some screenshots regarding the process. All right, so the final answer is x equals to 1.803. That's your final answer. Okay, so what was the value? The value was 1.03 to the power 20. All right, let's check using our calculator. Let's see how close we are. 1.03 to the power 20. 1.03 to the power 20. That is equal to 1.8061. 1.8061. Let's see what we got. 1.8061. Okay. 1.8061. 1.8061 is what we got. Look, 1.8061. 1.8061. This is what we got using the calculator. And see here, we using the log tables, we got 1.803. That is pretty close. The difference is coming at the third decimal digit, right? At the thousandth digit, the slight difference is coming, right? 0.003. That is the kind of difference that is seen, right? So it is pretty close. All right. Okay, let's move on. Let's now find the value of log of 0.0157 to the base 10 using log tables. So let's take x as equal to 0.0157 to the base 10. 0.0157, this is another type in which we need to move the decimal to the right. Okay, so to move the decimal to the right, I'll have to multiply that by 100 because I'll move the decimal 2 digits to the right to get the decimal after 1. So multiplication by 100 means division by 100. That means I will get, this part is going to give me 1.57 and this part will give me 10 to the power minus 2. Power of 10 gives me the characteristic. So characteristic is minus 2. Clear? Now 0.0157 equals to 0.0157. So ignoring the decimal, note that the value that is at the intersection of 15. Now look, in this case, you work on the significant digits, right? So here, the significant digits start from 1, and that's why I've added 1 0 over here. So first two digits will be 15. The third digit will be 7, and the fourth digit is 0. Okay? Please remember that. So ignoring the decimal, note the value that is at the intersection of 15 row and 7 column. We get 1959 as the mantissa. So log of 0.0157 to the base 10 is equal to characteristic plus mantissa. And mind you, here in this case, the fourth digit was 0. So we ignored the mean difference table. Okay, this was the fourth digit, 0. Therefore, we had ignored the mean difference table. All right, so we get 1959 as the mantissa. Now we add that to the characteristic. The characteristic is minus 2. So what we do? Minus 2 plus 0.1959, and we write that is in the bar notation form. That is, we read it as bar 2.1959. All right. So that's our final answer to log of 0.0157. Okay. Now let's do another question. Let's verify the result of question number 3. That means whatever we got before. Okay. Let's check whether anti-log of bar 2.1959 returns 0.0157. Mind you, look over here. See, log of 0.0157 to the base 10 gave us 2.1959. So anti-log of this particular number should give us 0.0157, right? So let's check that. To find the anti-log of bar 2.1959, okay, look at the whole part. The whole part is minus 2 over here, right? So the characteristic is minus 2. The fractional part is 0.1959. So first two digits are 19, second, the third digit is 5, and the fourth digit is 9. Okay. So look at in the anti-log table, note the number that is at the intersection of 0.19 row and 5 column. So you will get 1567. Okay, you can pause the video, look at the log tables, and you can verify that this number is correct or not. Okay, so you get 1567. Add the mean difference 3, which corresponds to the 4-digit 9. All right, so in the same row, the intersection between between 0.19 and 9 in the mean difference table, you will get 3. So add 1567 that you got before and 3 to get 1570. So now the characteristic point was -2. Okay, so add 1 to this characteristic. Okay, so to put the decimal, add 1 to the characteristic. So you get -2 plus 1, that is -1. Okay, so we need, now look, this is -1. That means we need to place the decimal by moving 1 digit to the left of the first digit, right? So we had got 1570, right? So we need to place the decimal by moving 1 digit to the left of the first digit. So that is insert 10 before 1. We had to shift it 1 digit to the left of 1. We had to move the decimal. So insert 1. So what you get is okay, insert 10 before 1, I mean. So you get 0.01570, which is equal to 0.0157, right? So we got 0.0157, and that is what we should have got, 0.0157. So our answer stands verified. Clear? Okay. Now here is a word of caution. While finding the antilog of bar 2.1959, please do not convert it into -2 plus whatever. Okay, that is -1.8041. Don't do that. The reason is that if you will use this format, then in that case, if you just take this, for example, if you take this first 2 digits as 0.80 row and then the fourth column, then you are going to end up with this number, and then mantissa for 1, you will get this. So what you will get is this number, which is the wrong result. So this is not recommended. It doesn't work like that. Okay, so this is a word of caution for you. All right. Now, after having seen 0 as well as negative characteristic scenarios, let's do one last example involving positive characteristic to wrap up the class. Okay. So let's find the value of log of 50.03 and verify our result by using anti-log table. Okay. All right. So let x be equal to log of 50.03 to the base 10. 50.03, I have to express it in scientific notation form. What I want the decimal after only 1 digit to the left. There should be only 1 digit to the left, right? That means after only 1 digit, I want the decimal. So I'll have to shift this decimal towards my left by 1 digit. How do I do that? By dividing this number by 10. So if I divide it by 10, I'll have to multiply it by 10. So what I get is 5.003 into 10 to the power 1. This is in scientific form, right? The decimal is there after the first significant digit, right? Balance all digits are expressed as a fraction, as a fractional part, right? And then it is in terms of multiples of power of 10, right? So characteristic of the power of 10, that gives us the characteristic. Okay, so we got the characteristic as 1. Okay, sorry, I beg your pardon. The exponent of the power of 10 gives us the characteristic. So we get our characteristic as 1. Clear? Now we have to find the fractional part of the mantissa. So look at the number. The number is, ignore the decimal. The number is 5003, right? Take the first 2 digits, 50, that as the row, and 0, the third digit, as the column. You will get 6990 at the intersection of 50 row and 0 column. Look at the mean difference table in the same row. The intersection between 50 row and the third column in the mean difference table gives you 3. Add the 2, you get 6993. So your fractional part is 0.6993. Add that to the characteristic. What you get is 1.6993. Clear? That is your final answer. Clear? Let's verify this. Okay. So log of 50.03 to the base 10 equals to 1.6993, right? So anti-log of 1.6993 should give us 50.03, isn't it? Log of 50.03 to the base 10, that is equal to 1.6993. And basically, it means that 10 raised to the power 1.6993 is equal to 50.03. That is, NT log of 1.6993 should equal to 50.03. I've repeated myself for the sake of it. Okay. So let's check. NT log of 1.6993. The whole part 1, that is your characteristic, isn't it? So add 1 to the characteristic. So now we know that we will have to put the decimal 2 digits. We'll have to shift it two digits to the right of the first digit, whatever we'll get as from the Mantissa calculation. Okay. So now to find the Mantissa, take the first 2 digits from the fractional part, that is 0.69 in the anti-log table, and look at the intersection with the third digit, that is 9 column. Okay. It will give you 5,000. All right. So the mean difference table in the same row, the intersection between 0.69 and 3 in the mean difference table gives you 3. Add 3 to 5,000 to get 5,003. Now to put the decimal, you know that we have to shift 2 digits to we have to shift it 2 digits from the left, right? From the left, we wanted to shift the decimal 2 digits. So the first digit was 5, the second digit is 0. So we want to put the decimal after that. So what we get is 50.03. Okay. Thus, we get the desired number. Let's check. 50.03 is what we should have got. And yes, we got this. Okay. 50.03. So it works. Hence it stands verified. All right. So I think with that, we will end this part of the class or video. And I intend to make another video based on logarithms as a sequel to this part. And there we will discuss how to calculate square roots, how to find cube roots using logarithmic tables. But primarily, actual usage of logarithms would be when you find something like 1.05 raised to the power 60 or something like that. Okay. When you use exponents. Okay. There the usage of the logarithmic tables is pretty pretty visible, and because for square roots there are other ways in which you can find square roots. So have a look at my second video. Maybe you first part and the second part combined will give you a very thorough idea, a very comprehensive idea on how to use logarithmic tables and the concept behind it and the arithmetic operations involving logarithmic operations. Okay. So I hope you enjoyed this video. If yes, please consider giving it a thumbs up. Please give it a like. And please subscribe to my channel in case you are interested in more videos such as what you saw just now. I would be posting content on mathematics, English, and soft skills. So if this interests you, please consider subscribing to my channel. Thank you so much for viewing this video, and I hope to see you in the next video very soon. Bye for now.